The break time is over, and I want to remind that the link for the certificate and feedback questionnaire will be shown at the end of this webinar. So please fill the form for your certificate. And we will continue this webinar with our next moderator. And without any further ado, please welcome Dr. Jimmy Chandra.
Okay, thank you, MC. Okay, good afternoon, ladies and gentlemen. Welcome back to our second part of our webinar, Precast as Structural Element for Seismic Region Building. So in the first part of the webinar, we already talked so much about the application of the precast concrete structures in Indonesia as well as in India. So in this second part of the webinar, we will talk more about the building codes as well as the research at the precast concrete structures. So my name is Jimmy. I am assistant professor at Petra Christian University. I'm currently also the head of the structural engineering laboratory of Petra Christian University. Okay, without further ado, I will introduce our first speaker for the session. It's Dr. David Fernandez-Ordonez. He is the Secretary General of FIB, International Federation for Structural Concrete, since 2016. He obtained his master and doctoral degree in Universidad Politécnica de Madrid, Spain, and he has worked for many years as a civil engineer in both construction industry as well as in the academic area. He involved in many FIB publications and also one of the contributors for the FIB Bulletin 78, Precast Concrete Buildings in Seismic Areas. The title for his presentation today is FIB and the Commission 6 Prefabrication Seismic Design of Precast Structures. So the time for the presentation will be 45 minutes and then will be followed by 15 minutes questions and answer session. Okay, good morning, Dr. David.
Good morning. Thank you very much for your nice presentation.
Okay, you can start your presentation. Thank you.
I will start my presentation. Before that, I would like to thank all my Indonesian friends and colleagues for this very nice organization, and I can see a lot of people coming in, and I hope that we can share some information that is of interest of the Indonesian engineering community. I will share my screen. I will start talking now. See if I can.
Okay, yes, you can see.
You can see it. Let me put in presenter mode. Okay, can you see the presenter mode? Yes, can you confirm? Yes. Okay, perfect. So I will talk a little bit about what the FIB is, a little bit about what Commission 6 in the FIB does. And,
the screen is still blank.
Yeah, I see a white screen, David.
Oh, really?
White screen.
Next,
it's only white.
Okay,
so.
I go to the next
page or
slide.
page.
There is a.
You don't see it?
No. Still white.
Okay, so let me go back, stop sharing, and I will try to share again.
You did not share a different file, probably.
Yes, I did.
Okay. Yeah, now it's great.
Okay,
thank you.
Now you can see. Okay, perfect. Okay, so I will talk a little bit about the FIB. You know the FIB. Many of you already know because we have here the main people of FIB in Indonesia. But FIB is a community of countries and engineers that. Around the world that we are trying to develop knowledge in structural concrete. No? And it's good to know that we are organized by countries. We have now 41 countries. In Indonesia, the national group is led by Han Aili, that we were talking just a minute before. There is a deputy, which is Januarti Jaya Eka Putri. And I would like also to say that you have a very active young members group. The convener of that group is Andri Setiowan, who is interesting because he is now working at the PFL in Switzerland, so I can see him very often in the lab sometimes. So it's very nice, very active people, and I hope that we can, with their help, can bring a lot of information to you, to all the engineers in Indonesia. I will also tell you that them and I will be very happy to bring any topic of your interest to a symposium or to a conference like this, or even to start a document working together. So this is something that we are flexible and we can always do. We have more than 100 countries, members from 100 countries, so we are quite spread. Even if the FIB originated originally, it was in Europe and in some countries, but now it's spread all over the world. So you can see that we have persons in many, many countries. And what I told you before, this is what we're trying to do. We are trying to really work in the field, which is well, it's a narrow but also a very deep field of structures and concrete structures. That means that we have let's say the best people in the world is working for the FIB in a sense of a non-for-profit organization. Everybody is working in a voluntary basis, and what we're trying to do is develop this knowledge and to give this knowledge to the people so they can use it to create better concrete structures. So you see that we really, this is our intention, and we do it in several ways, through different publications, through different events, and so on. We are organized in the main important thing is the General Assembly in the FIB, which is the countries. This is where the countries are let's say are represented. Let me put last pointer. This is the General Assembly, and then we have a very important technical council where all the technical aspects are defined. We have a meeting of this in this month, in September, the next month, and this is where all the technical decisions, all the technical informations are developed in that sense. And from the technical council, we have many commissions and task groups and working parties, more than 70 working parties all over the world working for different aspects. I cannot go in depth in each one of the commissions, but we go from the materials, from the concrete as a material or from the reinforcement as a material to the design or to a specific aspect, as what we are going to see today is the Commission 6 prefabrication. This is the commission where I personally also have worked for many years, because I was a designer and a person working for a precast company for many years. So that's why I have let's say my technical knowledge goes into prefabrication in the first place. We had in Indonesia another event going through durability, as you can see, and we have other aspects. We deal in detail about other aspects of concrete and concrete structures. You see here that one of our last groups is the young members group. We are willing that all the young engineers or professionals around concrete can get together, and you have a very nice group in Indonesia or even in the international group, and we're trying to do all this kind of information for everybody. Okay, and how we develop how we share the knowledge. One is the journal. You know, we have a journal. It's called Structural Concrete. We publish with Wiley. It's a professional publisher. Anybody can publish in this journal for free. And also in some countries we have agreements that some institutions can send their papers to the journal and publish them in open access. So if you are interested, there is some information. I cannot go through that today. The journal is doing very good. It's publishing more and more papers. Last year it was almost 3,000 pages. This year is more than 3,000 pages, with a lot of success and a lot of knowledge coming from all parts of the world. As you can see, Asia today is a very important part of the world as concrete structures, and we are having a lot of papers from Asia. And if you are doing research and you want to show it in the journal, you can just send it. It's for free, so you can try. We have a lot of papers from all over the world. We also have one possibility to publish in this journal is what we call the short project notes, because we want persons from practice. I mean, in this case, could be Precast Structures, to present there in a very simple way, 2-3 pages projects. And the best, if you know that to do a research paper, it takes time, it takes a lot of effort. But to these papers, which are simple papers, we are trying that practice people, designers, contractors can show their own works in these places. I sent here an example of a bridge in Japan. As you can see, just a short description with some designs. And if you want to share the nice works that you do in Indonesia with the rest of the world, this is a possibility for you. We also do bulletins, which bulletins are books, and we publish about from 4 to 6 books per year. And they have different levels of approval, from the most simple one in the commissions to the most complicated or detailed one that is the model code in the is approved by the General Assembly. That means by the countries. So all these commissions and task groups are working to develop works, and what we have is a different kind of documents, all of them related to concrete and concrete structures. You can see here very many different types, like externally applied FRPs for reinforcement of concrete structure, or floating concrete structures, or I don't know, many ways of having this information. The national member group receives these books, and after 1 year, we are sharing the PDF with the national member group. So the persons that are belonging to the national member group, that means fib-Indonesia, they can also access to the PDFs of the bulletins that are more than 1 year old. Now I will tell you something else. We are trying to help people to get to these books. So the FIB subscribing members can look at any of these books. So we are already going through 100. Can go through these books online through a viewer that we have implemented in the website. And there we have almost 500 documents also from the CB and the FIP. That means that the older organizations from the 1950s, that we have a lot of documents, a lot of information in the web page that you can, if you are a member, you can take it. Okay, and then we have the highest grade of our documents, that is the model codes. The model codes have been developed by the CB and the FIP, the older organization from the FIB. The last model code is 2010, as you can see there, and we are now working very hard to develop the 2020 model code that hopefully will have a first draft by the end of this year or the beginning of next year. And this is a very important document, because this document is a pre-normative document that is helping from the beginning to develop other normatives. In Europe, it has been used to develop the Euro codes, the different kind of way of different evolutions of the model codes have influenced a lot some of the normatives in Europe, for example, in Brazil, in many other places. It's a document that countries can use it for them. And now we have a lot of influence, we have done a lot of workshops. So we have what is coming from Asia and from other parts of the world, like Australia, America, and we are working very hard. I cannot stop here today, but it's good to know that in many cases, when you don't have in your own normative solutions, you can go to this code and maybe get help from what you can design if you have a specific problem. This model code that we are developing now, it's on new structures, that is like the model codes in the past, and also about existing structure, how to deal with a structure that is existing and you have to repair, or how to assess it if it has enough strength or reliability. And this is quite interesting, because it's the first time a document is done like this in the world. And then we have also the events. Our next event is the ICCS 21. This is sustainability event that is going to be in Prague. It's been done every 4 years. And well, I hope that someday in the future, it can go to Indonesia. Maybe, who knows? We also have an event for designers and for contractors. It's called the Conceptual Design. That is going to be also in September, in 2 weeks, 3 weeks from now. And it's going to be in Switzerland. The next one is going to be in Oslo. And then we have also the PSD symposiums that the next one is going to be in Rome. We do it every 2 years. And the Congress that we do every 4 years. And that is going to be in Oslo this year. So in most of these events, you can also attend online. So it's up to you if you want to get there. Also, the proceedings of these events are normally for FIB members in the FIB website. Okay, and as you know, we are also doing a lot of webinars like you are doing. We are recording those webinars and we are posting a lot of these recordings in the FIB YouTube channel. If you want to take a look, there is a lot of information, a lot of presentations in the FIB YouTube channels. Sometimes we present our bulletins in an event, and we post the presentations and the recordings there. So there you have also more things to look if you want to take a look there. Okay, and then I want to give importance to the young members group. Now the convener of the young member group is Motohiro Ono from Japan, as the same as our president that is from Japan. And any young members, I will tell you, get in connection either with the international or with your national member group. You have a very active member group in Indonesia. There was the last one of the last events I was there with you. And I can see that a lot of interest people, but we are really helping or trying to help all the young members to go on with their own organization, giving them support and giving them also a lot of freedom to connect, to get into any of the groups and to try to. We have a lot of young persons now involved in the work of many groups, and this is very nice. We are very happy with this. And then I will tell you a little bit about the Commission of Prefabrication. This is a commission, long-standing commission that comes from the 50s and the 60s in the FIP. Now the chairman is Stef Mas. We have two deputies, Witer Kostry from Poland and Larvi Senor from the US, from the United States. Larvi is also a member of the Presidium. And we are trying in this commission to develop and share a lot of information about precast structures all over the world. I will just go a little bit, as I have given you these slides. I will try not to go through all in detail, but through this commission, people from all over the world get together and try to discuss and see how people are doing things in other parts of the world. And we learn a lot. I have learned so much in this commission when I was in the precast industry, learning from the colleagues and learning from what is the experience from other parts of the world, because there are so many clever people all over the world, and there is always something you can learn from them. We have in this commission several groups. One is about hollow core floors. They have a document almost finished to replace the old document, and Steph is the convener there. We are developing one about quality control to give information about what the quality control is done all over the world, so people can, in precast factories or the controllers of the precasters can see what other people are doing, and there is a help to develop a quality control in a precast factory. Or sustainability of structure, that is a group that I'm leading with another Spanish engineer, Albert de la Fuente, that we are giving rules to design with precast structures with regard to sustainability, or the concrete towers for wind power generators with another convener from Spain, or precast concrete bridges that I will show you. We have published just two bulletins about precast concrete bridges with input from all over the world. Or the retrofit of precast seismic structures. This is the follow-up group of the former group that developed Bulletin 78, in which Professor Pampanin is a convener with Spiros Soukantas, who is a Greek engineer that just passed away last month, unfortunately. Very, very active engineer, very nice person. And concrete in tall buildings, that we will have a bulletin very, very shortly now with George Jones from Ireland. And we have also developing a group in terminology, or one that is going very fast about precast parking structures. So you can see there is a lot of work around precast in this commission, a lot of groups working. And this, I want to show you a little bit the documents that we have published already, and that they are available in the web page. Hollow core floors, mixed construction, that means different kind of materials working together, precast concrete in wood or in situ or steel, any other. Or the first document in environmental issues, or the first document in seismic design of precast concrete building structures. This is a general document, which is also very nice. Or precast concrete bridges. This is the first document on bridges. Now you will see that there are two other documents. This is a conceptual, a concepts or state-of-the-art document for bridges or railway track systems. Imperfections, this is very important for factories and for controllers of the factories to see what are the possible problems, what are the solutions, and goes into the quality control and how to assess if you have a crack, if it's important, if it's not important, how to deal with all those things. I think it's a very important document also. Or the very, very important document on connections, which is about design and execution of connection, a very big document that, as you know, in prefabrication, connections are very important. Affordable housing, how to design, what are the solutions for affordable housing all over the world, from India to South America to many other places. What are the solutions in Brazil also? Or design about accidental actions. You know that this is progressive collapse is one of the important things that you have to assess when you design precast structures, and this is how to deal with that. Or this handbook, that is a general design handbook, very important for architects or for design engineers that want. It's a conceptual design of buildings and it has a little bit of everything in it, and it's a very important book, for example, for schools if they're teaching also precast structures. And I think it's quite interesting. Has a lot of copies sold of this book, and it's given in many universities for master students in precast structures. Or we'll talk a little bit today about 78, the precast concrete buildings in seismic areas. This goes more in depth about the design of buildings in seismic areas. I will talk a little bit about the bulletin, and Professor Pampanin will tell you a little bit about the future evolution of precast structures in these seismic areas. Or how to design with real sandwich panels, that is a lot used in the Nordic countries where they have a lot of need of insulation. Or the sustainability, this is the group 6.3. We already published a document about sustainability. And we have another one about bridges, about how to design the continuity in bridges, which is very important in many countries. And this is design aspects of how to design this continuity in precast bridges. As you know, is quite complicated from the design point of view. And this is a bulletin, the last one from the Commission 6, that is a conceptual design. This is a big document that gives 30 examples on how in different parts of the world people are designing precast concrete bridges. From the US to Malaysia to Japan, Brazil, many places. And this is in print. We sent it to the print 1 week ago, and it will be available in 2 or 3 weeks for everybody. And the next bulletin that will come, it's this precast concrete in tall buildings, that from that group that I told you, the 6.7. And it's also a very nice document on how to use precast concrete in high-rise buildings. Well, this is a lot of information about that. And then, as you can see, there is a lot of interesting things going on around, but let's focus a little bit on in precast structures in seismic areas. And so this is a very typical design of precast structure in seismic areas. Okay, so I'm going to go through a little bit in Bulletin 78, not so much in design aspects because we don't have the time to go a lot in detail, but I will also go to show some examples of solutions that can be used. So what we have here is that I will go a little bit in general about the text because I want you to go and show some examples. So one important concept here is that precast concrete structures can be designed and built in seismic areas. No matter if they're small or high seismic areas, the matter is that you have to design precast structures in accordance to where you are building in seismic areas. So you need to design with the ductility, with the rigidity, with the same as you are doing with in situ structures. The precast concrete structures have more specific problems because the building is not built at once. Let's say you're building in a factory and then you're connected the building, but you need to be consistent with your design, and then you have to construct and to design your connections so that the building behaves as you have been designing. If there have been problems in the past in precast buildings in seismic areas, the same as in situ buildings, is because the design and the construction were not consistent with each other most of the time. So what we need in this time is that we need to be consistent. We need to define a solution of the structure that in precast structures we can decide two main ways of designing with precast structure in seismic areas. And then we have to go all the way in the design and in the construction and make sure that your connections, the connection of the different precast elements are behaving as you are designing it. So this is the main important things that you have to take into account. So if we know these main concepts, then we have to go down and define how we can design and build buildings, in this case in seismic areas. Okay, so the first thing that we have to know is that we have to assess what is the ductility of this building, because normally the ductility defines the forces. If you are defining by force, then Professor Pampanin will tell you a little bit more about this. Most probably is that you need to give or assess the adequate ductility for your precast structure. And that means that you have to be consistent. If you are having a very rigid structure, you have to deal with that in the design. And if you are having a more ductile or a more deformable structure, you have to define and see that. In some normatives, they say if you are a precast structure, your structure is non-ductile. And this is not true. Each structure has a ductility. The only thing is that we have to assess and be aware of what is the ductility factor of our structure, and then the behavior of that structure, let's say the deformation capacity of that structure. So we need to define it and be consistent with this definition for the design and the construction. And then we have to go along in the connections of that design. Okay, so we need to go in this sense. And here we are assessing about the New Zealand code, because New Zealand code for precast structure is a very advanced code. It is the first code that really deals with precast structures in a good way. Other codes were, let's say, reluctant to use precast structures, but now they are done in every country. Europe, for example, in Italy or in Japan or in the United States, which all are seismic countries and all are using precast structures. The only thing is that you need to be aware of how you do that, yeah? and you have to be consistent with this. Okay, so and then you have we'll go a little bit in that. You need to know where your connections are, how your connections are. So what you need to do is, for example, you have to have the connections outside of the critical zones, like this is the case A, or you have to have them inside the critical zones, but they have to be stronger than the rest of the solution. This is also a possibility. Or the other possibility, which is quite interesting, is to have the connections inside the critical zone, but you have to make them ductile. Or you have to avoid the rigid connections, you make them isostatic or make them hinge. So and then if you are consistent with your design, you can go on. Other important thing is that you have to connect every part of the structure, and everything in seismic areas have to be connected and has to be connected properly with reinforcement. And this is very important. This is just a model in the bulletin, so you need to see the connections and you have to follow the connections. We cannot go in very much in detail of all of them, but you have to see that you have to have connection between slabs, connection between beams and slabs, or in different ways. Or you can see here the different possibilities that you have to be aware that your different elements have to be connected, and you have to resist the forces that are coming from one to the other. So this is very important. Everything has to be connected, and everything has to be connected in a, let's say, mechanical way. Connection only by weight or by friction is not something that should be done in seismic areas for precast elements. I would say not even in non-seismic areas, but for seismic areas for sure not. Other important thing is just as a conceptual design is that you have to have uniform distribution of rigidity, and that means that you have to have uniform distribution of rigidity in plan and in height. And this means that you can have all the columns having similar rigidity, or you can have different ways of having coarse or rigid parts, but they have to be placed so that the rigidity is similar, because if you are imposing deformation and the rigidity is not the same, then you have concentration of forces. That this is what is bringing you problems. If you have a special shape, you have to be very careful with the special shapes. Even you can detach the special shapes, create simple shapes with joints, or you have to be aware that you have to have very high rigidity to be to take part of this special shape. Because when you have a special shape, you have torsion in plan, and this is you have to be aware that this is happening, and you have to be careful with this. But this is the same as is happening in an in-situ building or in a precast building. These are general design aspects of seismic structures, as you know. So you have to be very careful if you are not designing in a uniform way in plan or in vertical way. If you have one aspect that then you have less rigidity in one place in the bottom part or in another part, then there is concentration of forces in those places, and or deformation, imposed deformation in those places that can bring to fatal failures, like you can see in many other examples. These are examples in the United States, and we are learning from our own defects. So then these are mainly, it has nothing to do with precast or in situ. It has to do with the conceptual design of the structure, and we have to be aware of that. Okay, so these are examples also in the US that they are not scared of sharing when they have problems, and this is something we have to be very careful when we design. This is not a problem of the system. This is a problem of how you are designing that. Okay, so we have two main. I'm going to talk today about frame systems. That means that beams and columns. I'm not going to talk today about panels, but that panels are also possible in precast elements. And we have two ways of doing a frame system. One is to have hinges, and that means isostatic connections between beams and columns, or we can have a fixed connection between beams and columns. If we have isostatic connections, then all the rigidity goes to the foundation. I will go to the drawing, okay, like here, and then you have a lot of deformation. You have more deformation in the building. So these kind of buildings, you can use them for not very high rise, but you have to have all the rigidity, all the ductility goes to the foundations. So this is something very important. You have to be aware of that. You have to have very strong columns because all the ductility, all the moments go to the base of the connections, because the connections between beams and columns are isostatic. So this is a possibility. This is a possibility for certain type of buildings, not very high, not very high loads. So you can also have these solutions, and this is done 2-3 levels, and then the columns become bigger. But they can be done, and they are ductile enough to, so they are designed in many places, like I told you, in the US, Italy, in many other places. Okay, and you have to have connections that go through the different part of the beams and the columns, and you have to be aware that you have shear forces going through these elements. You have to have also bending moments because of the torsional moments, because of the forces that are coming, horizontal forces. So these connections, even in isostatic, they have to be well connected, well designed. If you have a shear force, these bars, they have to be resistant to those connections, and you can define this resistance with this bulletin that we talked before about connections. No? So this is one solution. And you can see that every connection, if you are talking about the industrial buildings, they have to be connected. And also, very important is not just that you have a bar, that you also need internal to make the force that goes from the bar to the rest of the connection. And this would be another dissertation about connections. The force that is in this bar that is coming from another element, we have to make sure that goes to the rest of the element. And that means that we need confinement, reinforcement, mostly in all the end of these elements. And we're still only talking about isostatic. So it's only about even the most simple way. We have to be aware of how to do this confinement and how to do these connections. Yeah? And then we have to go in the detail of the connection and the construction of the connection. And then we have the moment resistant connections that are, let's say, the most common for higher buildings in seismic areas. And that means that we have to pass all the moments and the shear forces in these buildings. And then, of course, the deflections are smaller because we are sharing the moments and between the foundation and all the connections between the beams and the columns. Yeah? All the building is sharing these forces. Yeah? And then, of course, we could have a third way of doing this, that to have a rigid course and bringing all the forces to the rigid course. But okay, and then we have to assess all these moments that are coming from the beams to the columns, and then we have to be sure that these connections are ductile or they have enough strength to assess the full ductility of the whole building. Okay. Also, we have to be aware that all the connections are really passing all these forces. And as today we're designing, we are assessing ductility, and we are allowing ductility, and Professor Pampanin will tell you what happened in Christchurch when we are designing just with ductility, and if we want to have a building that is working after the earthquake, not just resisting the earthquake, but working after the earthquake. But today, we are just assessing that the building is not collapsing, is having enough ductility, is resisting the earthquake, and that means that we have to assess that. There is lots of research going on I would say mostly in China today, about different solutions of seismic aspect of precast elements. If you can go to our journal and take a look at there, for building, for beams, for columns, for panels, for many other solutions. Okay, and then we have to see if we emulate this ductility as an in situ building, or we change the solutions with different other ways of building, like bringing the, as I told you before, bringing the connections outside of the connection of the between the beam and the column. Okay, and there is one solution that is a hybrid solution that I will not go a lot into this, but Professor Pampanin will talk to you a little bit later. Is that have ductility through unbonded tendons and unbonded mild reinforcement, and this is something that has been started in the US with the press systems, and it has a lot of importance, I think, in the future, because it will allow the building to rock and to move without a lot of deterioration of the connections, and this is something which in the future it's very important, and Professor Pampanin will talk to you a little bit about that. And I will use my last minutes to talk a little bit about different solutions. And this is just ideas that you have in Bulletin 78. There are many others, and you can even design your own ideas. These solutions are given here to help you find solutions of what other people are doing in the world, and this is a connection between a column and a beam, in situ connection, and we can see some reinforcement coming outside of the beams, and then we are going to do a connection that is completely in situ. We have precast column, precast beams. We finalize the connection in situ with the stirrups, with the overlapping of the positive reinforcement, and then we put the hollow core slabs, and then we put the negative bending moment reinforcement on the top, that it's on the topping, and then you can see the reinforcement for the beams and the reinforcement for the slabs. So this is one solution that it's quite interesting and maybe interesting to use, but every country is different. You can define your own solution, and these are just ideas. And the most important thing of these solutions is that you can see what is possible and what has been done in other places of the world. And you can see here the placement of all that. This is a similar solution, but to putting the beams on the corbels, so you can have more space for the support. But I will go a little bit further. This is a solution with a U-beam that has been used in the first place in New Zealand, but this in other places too. That means that you have a U-beam here, and then there is a in situ core of the beam and in situ reinforcement that is being done later on. The column can be in situ or can be precast also, and then you finalize all the connection in situ. You can see here the overlapping of the bars. And then you can put, this is a floor with hollow core slabs, but could be with planks or could be with other solutions. And you can see here an idea of what it looks, a system like this with the beams. Of course, everything is complicated because you have to have reinforcement coming out, you have the positive reinforcement coming here, you have the negative reinforcement that is coming out of here, and then you have to finalize the solution. And then you can see here, precast solution here, precast beams, and then the fully in situ rest of the structure. And then you are doing, let's say, a hybrid solution between precast and in situ. Okay, this is another solution in which the beam has a form that goes into the connection in ducts, and then you're taking the main connection between moments. You're taking it out of the main part of the column and beam connection, as you can see here. You are placing this, and you're creating the connection outside of the main where the main moments are that are here. Okay, so you can see here the beam, the sticking out the connection, the slabs, and the in situ. You have less in situ concrete in this place. You can see here a solution like that, a beam, a column, sorry, and a beam coming out all the way. So you are having the connection outside of where you have the main moments. So this connection will be, let's say, with less reinforcement, easier to do. Well, maybe difficult in one way, but easier in another way. As I have finished more or less my time, I have other solutions here in my presentation that I make available for you. So I think I will stop here, and I will let Professor Pampanin talk about other hybrid solutions later. And maybe I would give you the time for questions, because you told me before that there was a need more time for questions. So I think I will stop here, and I will allow this time for questions. So I pass the word to the chair of the session.
Okay, thank you, Dr. David, for the interesting presentation. So now we are entering the questions and answer session. For those of you, if you want to ask a question directly to Dr. David, you can raise your hand and then turn on your camera, and then we will unmute you so that we can have a discussion with directly with Dr. David. Or if you prefer to write down your question, you also can write your question in the chat room, whether in English or in Bahasa, so that I can try to translate for Dr. David. So is there any question from the audience you want to ask directly to Dr. David? So, okay, we still while waiting, there is one question here in the chat room from Dr. Nugraha. Dr. David, have you an experience about the combination between precast concrete structures and base isolation in the high seismic region?
Yes, well, this is a very good question. I do not have personally seen this in any place. Maybe Professor Pampanin has more experience with that. What I have seen, and we have seen experience, is to use precast structures with dampers. Yeah? And for that, I have seen several solutions, one of them in China, other one in Japan. And Professor Pampanin will for sure tell you about that for what he's talking about. But full base isolation in a precast structures, I have not seen it. So maybe there is, but I have no experience with that. So, but what you can use, no problem, is with dampers. I've seen, for example, in Japan, a building of 35, Japan in Tokyo, highest seismic place in the world, we could say, or almost, no? A fully precast structure with rigid frame and up to 30 stories. They are not isolating, at least for now, that I know.
Okay, thank you, Dr. David, for the answer. I think we can move to the second question from Mr. Andreas. Dr. David, concerning the in-situ connection between members, are there some recommendations to ensure their being monolithic, especially for the beam column joints, which are subjected to a large demand of force and ductility?
Yes, well, there are many possibilities. Where, of course, I've shown you a solution. A solution is to create the same reinforcement that you have in situ. You can use precast, for example. Let me show you in this case. Let me show you in this case the one that I showed you before. Let me just.
Yeah, you can share the
I'll share my screen. I'm looking for the screen. In this case, I will share my screen. I will not put it in presentation mode. Okay. If you see here, yeah, you can see that you have an overlapping of the bars on the bottom, and this is a possibility to overlap the bars on the bottom, and the bars on the top, they are directly the same bars as you have in situ. So this is one possibility. Another possibility is that the one that I show you here, in this case, in which the bars in the bottom and the bars in the top are directly the bars and in situ. So really the ductility of these solutions are, let's say, the same as in situ. There are many tests about different solutions, and I would say, if you are, for example, if you of course you can get the same ductility or even better, even with couplers. I've seen solutions with couplers, directly with couplers, and then you can get enough ductility. The thing is that you have to allow for enough anchorage, enough overlapping length for the bars that you are doing that. And of course, I have seen many solutions that have been tested. And imagine that you are doing a new solution, that you want to define a new solution that is your invention. What I would do a test to check that there is no problem, but not a problem with the system, a problem with the overlapping or with the connections that you are already doing. So normally the precast element has a higher strength concrete than the in situ concrete. So if you are sure that the in situ concrete is good enough, you have the same ductility, at least the same ductility that you have with in situ.
Okay, thank you, Dr. David, for the answer.
Sorry, let me just say one more thing.
Okay.
In Japan, the solution that I have seen with beams and columns, high, more than 30 stories, the solution that they used in this case was with couplers. So even without in situ concrete, even with couplers, you can achieve enough ductility. Sorry.
Okay, thank you, Dr. David, for the answer. Is there any question from the audience? Okay, this is one more question from Mr. Junata. Dr. David, when you use a hinge joint between beam and column, how to get the frame stability?
Yes, you get the frame stability, and you're looking at this. Okay, you're looking at my screen, no? All the stability, if you're using hinge, goes to the foundation. So all of it goes to the foundation. So you have to, the columns in this solution have to be bigger, and you need to assure that the connection in this foundation, that you know that there are several connections possible in the foundation of precast elements. One is the pocket foundation. Other is with bars, protruding bars with ducts, or even with couplers. You need to have enough anchorage length, enough ductility in the connection. The column has to have enough tie bars to allow for that. So in these solutions, all the ductility goes to the foundation. Okay. There has been many tests in the ISPRA laboratories in Italy to test the ductility and the ductility factor of these structures. And there is also a lot of information about that they reach enough ductility if the design has been done correctly. It is very important. Of course, you have to pass all the forces through the connections of the hinge connections, and this is very important. You cannot just put one thing on top of the other, and the forces have to connect beams and columns together and floors. And also it is very important that the confinement and the anchorage of the bars for the connections are properly done. It is very important to do these connections properly. And for this, you can also take a look at Bulletin 43 on how to pass these forces through the bars to the main part of the element, and this is very, very important.
Okay, thank you for the answer, Dr. David. For the next question is from Mr. Robert. The question is, how is the behavior of strong column weak beam mechanism in precast building in seismic region? Which one is the best in terms of seismic resistance between fully precast, fully in situ, and hybrid building? That is the question.
Well, the definition of weak beam or strong column is the same in situ and in precast. In precast, we have one thing that it's a little bit more complicated in one way, is that normally in precast structures, we are trying to have long spans. Long spans means that we are having strong beams. So normally in precast, if we are not in seismic areas, we are trying to have the longest spans possible because it's better for the structure. But if you go to seismic, you have to reduce the spans because the beams cannot be too strong. But this is not a matter of precast or in situ, it's a matter of the, design. You can design precast with weak beams or small beams and strong columns, the same as you do in situ. So for me, this is important, that this is not, let's say, the material or the solution of precast is not the problem. The problem is how we use this language, that is the precast language, okay? So we cannot design the same precast building in seismic areas and not seismic areas. That means that maybe we cannot go to such long spans and we need to go to shorter spans because we need beams that have enough ductility in that sense, okay? And I don't see any best solution. I think there is a best solution for all over the world. There is a best solution for your problem, for your building, for your in Indonesia. The best solution is different from Italy or from United States or from Japan. It is completely different. So you have to take into account the industry, the design people that you have there, the contractors, and taking into account all these parameters, then you define which is the best solution for the whole building. So I think you can use in situ, of course, you can use fully precast, of course, and you can use hybrid solutions. It depends on what is best. For example, Professor Spiros Soukantas, he was Greek, and he was designing buildings in Greece for seismic action. He went to work for many years to India, and the buildings he designed in India for seismic actions were completely different than the ones he designed in Greece. It's not because they were better or worse, it's because the industry, construction industry, the uses, the ability of the persons, the possibilities that you have are different. So you as designer have to see what is best for your case, and then you have to use your language, your solutions, and then comply with that.
Okay, thank you, Dr. David, for the answer. I fully agree with the solution. There is no best solution for all cases, so we have to look uniquely for each problem. So for the next question is from Mr. Andreas. The question is, in addition to using higher strength concrete, is there any recommendation regarding the grout, let's say using non-shrink grout or something else?
Yes, normally the grouts, for me, of course, they have to be non-shrinkage. And non-shrinkage, you know that non-shrinkage means that they include some additives to make them a little bit expansive, because concrete normally has shrinkage, so they add some additives to make it neutral in that sense. And this is very important, very, very important, because the anchorage in the grout depends highly on that. Second important thing is, well, of course, it has to have a high strength. I would say at least 70 or 80 megapascals at 28 days. But the very important in the grout for contractors is that at the next day, you can have at least 25, 30 megapascals, because you want to keep building. If you want to keep building, you need a grout that grows up very fast so you can keep building. And normally this is enough to keep building. And then what happens is that at 28 days, you have more than enough of what you need. So the strength is coming, not because you need the strength at 28 days, it's because you need the strength at 1 or 2 days. But I would like to say here that the future, maybe not today, but maybe in a few years, is to use ultra high performance fiber reinforced concrete for the connections. If you use this kind of concrete for the connections, or you can allow to make very high strength, you can take away some of the reinforcement or many of the reinforcement, and then all the connections can be very small and can be and I think the mix of precast elements with ultra high performance fiber reinforced concrete connections is something that it's to be used in the short future. Some people are already using it now, but be aware of that, and maybe you can design good connections with this material.
Okay, thank you, Dr. David, for the answer. There is still many questions, but due to the time limitation, we need to stop here. Please give applause to Dr. David. Thank you, Dr. David. So for the